So a z-score describes, as we talked about, how many standard deviations a data item in a normal distribution lies above, which would make it positive, or below, which would make it negative, the mean. The z-score is obtained with this formula. A lot of times I'll just write it this way. Z equals the data value, which is x, minus the mean, which is x bar, divided by the standard deviation, which is Sx. Data items above the mean have positive z-scores, and data items below the mean have negative z-scores. The z-score for the mean is 0. I asked you that in the previous problem. So without drawing the graph here, we're going to calculate the z-score of 92. Well, here's the z-score formula, and 92 would be the data value, the data item. What we still need are the mean and the standard deviation. So they give you the mean and the standard deviation up here in the stem of the problem. The mean is 60, and the standard deviation is 8. So the z-score for 92, this is how the calculation would go. Z equals the data value minus the mean divided by the standard deviation. So just plug in the three numbers that we know. The data value is 92 minus the mean, which is 60, and then we divide by 8. So this is 28. Now what is it? 32. 32 divided by 8. And so the z-score is 4. Well, maybe I'll do 30. Z equals 30 minus 60 divided by 8. So data value minus the mean over the standard deviation. Sometimes your z-scores will get into negative territory. So when you divide that, you're going to get a negative, and then 3.75. If you have two different tests and you want to compare apples to oranges because they're different tests, so they might be harder. For example, a physics test and an English test. One might be harder and the scores might be lower. So the mean would be lower. Maybe the standard deviation is lower or higher. And then maybe on the English test. So what if you scored, say, 90 on an English test and 50 on a physics test? What score would be the higher score? Relatively higher score, if the teacher is grading on a curve. In this case, the normal curve. Well, you can answer that question if you knew what the mean and standard deviation for each of the two tests would be. So let's take a look at this one here. Up at in the stem of the problem up here, you can measure intelligence, IQs. On the Stanford Binet, I'm not sure if that's Binet or Binet, intelligence tests are normally distributed with, okay, so the Stanford Binet gives you a mean of 100 and a standard deviation of 16. The intelligence quotient can be measured in a different way by the Wechsler, I think, test. And it has a mean also of 100, but it has a standard deviation of 15. So let's take a look at number 58 here. Use z-scores to determine which person has a higher IQ. An individual who scores 150 on the Stanford Binet test, or someone who scores 148 on the Wechsler. So the way that we're going to decide who has the higher IQ is we're going to calculate the z-score for each one of these different scores on the two different IQ tests. So for the 150, we're using the Stanford-Binet, where the mean is 100 and the standard deviation is 16. And the 148 is on the Wechsler test, where the mean is 100 also, and the standard deviation is 15. So we're going to calculate the z-score here. It's the data value minus the mean divided by the 16. And over here, our data value is our IQ score on this other test, 148 minus 100 all over 15. So the way that we will reason is that the score that has the higher z-score will be the higher IQ score. Two different people. So one person scores on one test, the other person scores on the other. All right, so when you take 50 and divide it by 16, you get the z-score of 3.125. This would mean that this person is very, very smart because they're more than 3 standard deviations above the mean, and only 0.15% of all humans are in that range. Over here, we would take 48 and divide by 15, and this would give us 3.2. So 3.2 is higher than 3.125. So therefore, the better score would be the 148, even though it's lower than the 150. So this is the better IQ score. So maybe we would say that that person is the smarter of the two. So z-scores are used to compare apples to oranges in normal distributions. Okay, we're going to turn the z-score formula around a little bit. So if we have z is equal to x minus x bar over sx, there's a way that we can alter this formula. If you multiply both sides by the standard deviation, the standard deviation over on this side will cancel. And then if you want the x by itself to find the x score, we'll add the x bar. So those would cancel. So we would get the data value we're looking for is the one where we take the mean and then add it to the z-score times the standard deviation. So that formula is the same as this formula. It's just manipulated by algebra to make it look a little different. So there's a couple of ways that you can do this one, and I think what they want us to do here is to use this formula. And so x is equal to x bar plus the z-score times sx. So they're saying what data value is 3 standard deviations above the mean? When they're asking for a z equal to 3, that's really what they're saying. And up in the stem of the problem, they tell you that the mean x bar is 400 and the standard deviation sx is 50. So they give you those two pieces of information. Then they say for a z-score of 3, so let's put in x bar is 400, the z-score is 3, and the standard deviation is 50. 400 plus, this is 150, would be 550. And you can see that, right? If the mean is 400 and the standard deviation is 50, then this scale would look as follows. Like this. And then if you attach the z-score as another scale kind of right on top of it, it makes sense that if you have a z-score of 3, that the data value that corresponds to that is 550. And that's the same thing we found here. So I would encourage you to draw this scale every time for every one of these problems, because a lot of times you can figure out the answer to these very quickly if you have this scale here. So look at the scale here and then write down the data values in each case. What's the X value for the Z-score of 2.5? What's the data value that corresponds to a Z-score of -2? And what is the data value that corresponds to a Z-score of -1.5? So you can use the formula, or you can just look at this grid to determine it. 2.5 standard deviations would be here. You can see that right between 2 and 3 would be 2.5, and right between 500 and 550 is 525. -2, 1, 2, there it is, 300. So this is equal to 300. 200 minus 100. And 1.5 standard deviations below would be right here, somewhere between, directly between 300 and 350, be 325. Okay, so the last thing in this section is just giving you a sense that, you know, not all data distributions are bell-shaped that look normal. Sometimes the data distribution looks like this. And then here's the tail over here, and the tail is to the right. So we call this skewed right. A lot of times the negative numbers are to the left and the positive numbers are to the right. So sometimes it's referred to as positively skewed. Let me think of an example. How many miles, when you're driving to Delta's campus, how many miles do you drive? And let's assume that we asked, say, 1,000 students that attend Delta College, how many miles does it take you to drive to campus? If you were to do that, you would find a graph that looks like this. Because most students, because they go to Delta College, they live close to Delta College, right? And so this would be 0 miles from Delta College. You know, the 3 counties of Midland and Bay City and Saginaw are all within a 20-mile drive. And so most everybody's going to be here, but then we have those students that are commuting in from Alpena and from the Thumb, but there's not as many of them. So here's an example of a data set that would lead to this skewed right distribution. And if you see a data set that looks like this other one, over here is the tail to the left, and we call this left skewed. An example here would be student GPAs. Student GPAs. The highest GPA would be 4.0 and the lowest GPA would be 0. And most students, if they are enrolled at college, most of the GPAs you would find, let's see, 2 would be right here. Most of the GPAs would be in here. In fact, maybe from 3 to 4. And very few students have GPAs that are out here. Most of the GPAs are clumped in this area.